Hi everyone, welcome back to another series of the NL seminar. After some summer break, now we're back to inviting people to give us talks. So I'm really excited to be back here in person. Today we have Mitch, Mithun. I didn't put your last name, but to give us a talk on phishing emails, improvised explosive devices, and quantum, a natural language understanding perspective. So Mitch was a postdoctoral researcher at ISI, where he was working with Marjorie Friedman and Ralph Wishdell in the networking and cybersecurity division. Mitch graduated from his PhD from University of Arizona, along with his master's in computer science before joining ISI as a postdoctoral researcher. Before that, he worked in the software industry for 10 plus years as a product manager in a research lab. He also has a master's in physics from Berla Institute of Technology and Science. His research interests include natural language processing, cybersecurity, and quantum computation. I've heard Mitch mention quantum a lot, but really didn't get the chance to learn about it. So I'm super excited on what he has to share today. So without further ado, please welcome Mitch.
Hello. Today is my last day here at ISI, so which is why I was a postdoc. He's a postdoc and will be was in like 8 hours. So yeah, welcome. Essentially, I'm going to talk about 3 projects I did the last 1 year that I was here. The first one is a project I did with Jen, who is here, and a lot of other people about phishing emails and using natural language understanding. Then I'll talk a little bit about this other idea, which we worked about, likelihood of complex events happening. And I'll also talk a little bit about the quantum work I did in quantum NLP and end with the future work. So let me start with the phishing emails and the natural language understanding part of it. So the question we asked ourselves was, it has been 35 years since the first phishing email came out. Why do we still fall prey for it? Like even now, one of these very smartly crafted emails shows up in your inbox and you for a second think it is real and you respond to it. So how can we help people and machines not fall prey for it? Yeah, so more importantly, why do people still fall prey for it, right? So why are people still reacting to it quickly? Or, an email like this comes up, you say, hey, there's a problem with your preferred payment method. Can you send your credit card? So you're probably like smart to not fall for that. But the more interesting thing is here we are dealing with humans writing emails as opposed to machines writing phishing emails. So humans are smart. And now we have another human trying to read it. And this is like a cat and mouse game between the humans. The question is, we always have this thing, the email spam inbox filter. So why are these phishing emails passing through the spam or phishing filter emails and coming to your inbox? And why are you falling prey for it? And what can we do about it? So that was the first question we asked. To arrive at that answer, we've had a collective cybersecurity and natural language understanding experts. And what we did was we got a bunch of data sets. First was the Enron corpus, which was about the emails that happened in the Enron company. It came out around the year 2000. Then we collected phishing email corpus, which was only phishing emails. Enron was just a regular email data set about people who were working at Enron and how they communicated with each other. And to get more phishing-like email, we contributed from our own spam folders. So the goal here is not to create a system which identifies phishing emails, but to understand what is going on. So after a lot of deliberations, we came with this 32 labels. You don't have to read all that. I'm going to get into this in a second. So these tables are things we found was very commonly occurring between regular emails and phishing emails. So if you think about it, the machine learning model is trying to look for cues, the filter that is sitting there. And for some reason, it's missing stuff and it's showing up in our inbox. So we thought, which ones of these might be sensitive thing for the AI filter and which one is the one which humans react to? So let me give you a few examples. So these are categorized based on the level or the scope of the labels. There are a few at a message level. For example, the first one is message PA, which is a message from a person asking for performing an action. So this came out after like 4 years of the cybersecurity experts looking at phishing emails. This is essentially their intuition. Something at the sentence level is, hey, let's say the sentence talks about offering money. So that is very common to phishing emails and regular emails. So how do we distinguish between both of those? The same at the signature level, word level, etc. So now let me take an example, right? So here's message level labels. So the first one is message from person asking for performing an action. So now, for example, here's a message says, hey, please let me know if you have any questions, right? So this is a typical message you get from your colleague. It's a person asking for performing an action, but it is exactly how the phishing email is going to craft. The phishing email writer is going to craft his email. Come give me a call. So it's a very subtle thing that's going on deep in there.
Is this a phishing email or not?
This is a regular email. So it's just a regular email, right? So it's not a phishing email, but I'm just showing you the trickiness here because it's very close to how both these emails are very close to each other, right? This person asking to performing an action happens in both the cases.
Wait, do you have an example?
For the phishing one?
Yeah.
Not yet. No, probably there's somewhere I can pick it up. Just give me an example of sentence levels ones, right? So here's one which says sentence asks the recipient to click on a link. So to log back in, you need to set a new password to the link below. So if you think about this is exactly the same thing a genuine email and a phishing email is going to ask, right? How do you distinguish between these kind of things? Signature level ones are at least very much straight on your face. Somebody puts their signature down there. And I'll tell you in a second why we are focusing on a signature level one. The only reason I show you this is these are the signature level ones, like we look if the mailing address is mentioned in the email signature, is the full name mentioned, job title, etc., etc. What can we gain from the signature emails? Word level, kind of pretty similar, but here's somebody saying, I do not expect to get to Houston until about 9:30 p.m. So from which we can gather that this is a sender's current geographical location or somewhere he's going to be in a given time. So these are a general category of labels which we arrived at. Now, why did we pick all these kind of labels, right? So this is the intuition behind it. In emails, there are two kinds of information. The first one is the information that can be falsifiable and which can in turn be verifiable. Typical example is your signature block. So everything a person writes in the signature block is, you can verify it against a data source. You can either get the mailing address of the person or his job title, simply put it in the LinkedIn API. If that verifies, oh yeah, sure, this is verifiable information. So that is one thing which we realize is possibly doable when we look at a phishing email. If somebody claims he works for Bank of Nigeria, that is something you can verify. The definition of you is still machine or human. Another intuition was, what is the content and tone of the email that is very subtle and gets you all the time? Right? For example, sentence has a polite tone, extremely polite for no reason, extremely urgent for no reason. So those are like usually a telltale sign of phishing email, but it can go both ways, right? So somebody is just being nice. So those were the two broader intuitions we thought of when we came up with these labels. Now, here's an example for the urgent one, right? So I am Mr. Chukoi, Director of Operations of Hang Seng Bank. I have an urgent business suggestion for you. Now, if you think about it, if it was there are two ways of an email you'll get. Either you know the person, right? And the person is saying, hey, we met somewhere and I have an interesting business suggestion for you. Or here is a new person messaging you. So this looks perfectly phishing email, right? On the other side, this could actually be a new proposal coming from a new person, So does urgency always mark? How do we even know urgency means phishing and non-urgency is not? So this is a very complex problem to simply put. So what we did was we got a bunch of annotators and we gave them all these emails in this particular interface. So what they were doing was look at each of these emails and start marking them to one of these 32 labels. For example, hello, my name is Sarah and I work for Facebook as a marketing manager. So that one sentence, it's marked as message contact person asking. So basically the person who is contacting you is asking you to do something. And it also says message contact person org, which is essentially standing for a person is representing an organization, the yellow one is sentence intent intro. So the person is giving an intro for himself. And again, so now we also see word center organization, which is marked for Facebook. So now we know this person is working for Facebook. So this is how we slowly gathered all these different levels of information. So what do we do with this kind of information? So that we haven't yet gotten to downstream tasks. So this is still the place where we are gathering this information. Same thing with like signatures, where you have, here's a signature, what can we get from it? Job title, organization, address, etc., etc. So this is especially interesting, like I mentioned, in the verifiable side of things. So goal here, like I said, is not just finding characteristics found in phishing email, but characteristics found in all type of emails. And now you're going towards which one of them is easy for humans and which one is easy for machines to identify. So that was our goal. How can we reformulate the training mechanism of machine learning and human learning as far as phishing email is considered? Here are the results of performance. So essentially what we did was we trained models like BERT, Robert Large, and etc. on these labels to how good are they at identifying. We also got humans to annotate this. Like they look at the label and decide, oh, this is polite, this is urgent, etc., etc. Even here, we had a bunch of interesting disparities. There were labels which both the machine and humans were good at recognizing. For example, messages where sender is asking the recipient to do something. So if you can see the performance, most of the machine learning models and the inter-annotator agreement, the human agreement, are able to do it correctly. So sorry, your question?
Are these spam identification as well as labeling, or just labeling?
So this is span identification also. If you look at the actual, this one here, so they are identifying the span of the word, they're identifying the span of the sentence.
Exact mention.
Yeah.
And so this presumably the numbers that you're showing are estimated.
Yes, these are the estimations at this point. So, so coming back to this, so the solution here is, if there's a label that both machines and humans are good at recognizing, let's do more training, offload that job to an AI model, which can be trained to identify that more. Here are some labels which humans are good at identifying while machines are not. Surprisingly, the sentence level labels, as you can imagine, like somebody selling a product, and if you look at sent PR, you can see all the BERT, Robert, everybody, the performance is really dire, while humans have 0.98 inter-annotator agreement. So this one, humans are good at it. So let's give this task training to humans. That is a downstream possible implication of this result. There is some which is equally hard for both machines and humans. Politeness, urgency. So this is the tricky one. How do we deal with this? So this is a training which both humans and machines have to be trained on, identifying politeness and is this phishing or not. So the goal, like I said, ultimately was to create directions for differentiating between things which the humans are good at and which the models are. So that was my first project. So that is a natural language understanding perspective of it. And there is an underlying theme here, which I'll get to in a second. This is the second project I worked on. We call it likelihood of complex events. So this project asks questions like, if a person is buying 25 pounds of ammonium nitrate, what is the probability that he's going to commit a suicide bomb attack? Can we raise a red flag at that point and tell people that, hey, this is going to happen. This particular person is trouble. Same thing. If a person is buying an assault rifle, what is the probability that he's going to commit a mass shooting? Or if people are just gathering for a protest, what is the probability that it might turn into a riot? So how do you answer these questions? These are all these events on the right are called complex events like riot and suicide bombing attack. But the core of the idea here is, while individual preferences differ, almost always there are a set of standard events that happen in all these cases. For example, typical events in a riot are people gather, rioters destroy property, rioters attack police, police attack rioters, so on and so forth. So this idea of grounding the probability using a schema. So what we're doing here is called a schema. Schemas are essentially a scaffolding or a skeleton, which writes down all these individual events that typically happen. And currently, schema curation or the creation of schemas happen in a hand-in-hand methodology where we ask a large language model to predict one of the typical events, give it to a human and understand it, how it happens, right? So this is what we call, we are using schemas to answer the likelihood question. So this is a typical schema for a riot. It's complicated because it has temporal things that can happen. If you look at the actual schema, this is how it looks like. There's so many events which happen at the precursor, the actual event, and after the event. So the question we had was, okay, we have a schema created by human curators. How can we answer the other question, which is, given one of the events, what is the likelihood of a big event happening? So the way we formulated this was a Bayesian methodology, where we said, if the probability of a schema given an event, if we can calculate, we can calculate that using if we can find the probability of event given schema and the probability of schema and event. So for example, if we can find the probability of people gathering given that a riot happened, and the probability of a riot happening, probability of people gathering in general, we can use that to find the probability of riot given people are gathering. So, sorry, yeah.
So I had a question about, like, when you're defining the schema, how do you set the ground truth on what counts as the riot? Or for example, some people would say that tear gas is a crowd control measure. Some people would say that it's attacking protesters. So who gets to be the arbiter of what's the ground truth on?
Yeah, so this was a 5-year project exactly just to answer that question. Like, start with one event, okay, then somebody comes in, but here are a bunch of exceptions. So then we expand the schema, and the initial schema becomes a sub-schema. So a lot of iterations happen between curators and subject matter experts. A lot of discussions happening, guided by DARPA's needs at that point. And that's how this list was arrived at, which tries to capture almost always the events given a definition, right? Like I said, if we start with a smaller event, like you said, the crowd control alone, and then people say, oh no, that's always part of a riot. So we bring a bigger schema in for riot, of which this becomes smaller part, which is why I'm showing you this picture, because of which there are so many complex sub-schemas inside it. So the problem with this is, we cannot do a probability calculation like this with just this handful of schemas. Like I said, creation of schemas is a human time process, and human is the actual bottleneck in there, because for 5 years we went back and forth discussing and trying to decide what is the right events that should go in a schema. But clearly that's not scalable, right? And left alone for a probability calculation. So what we did was, so this is what I said, like currently we are limited by the schemas because human annotator is a bottleneck, and there are only like handful of complex events for which there are well-established schemas to which people agree. So this is a typical pipeline, like we use hand in hand, we use large language models. For example, this is a prompt we ask GPT. These are the events that typically happen in a riot in that order. People gather, rioters destroy property, etc. Predict a first event that happened before the rioters destroyed the property, and GPT says, oh, social unrest intensifies. So we take that output, give it to a human curator, and with an inter-annotator agreement, we decide, okay, that seems like a good one to add. So that's how this whole curation process happens. Now, solution we came up with is, can we ground this against a well-known news corpus? Say, like I said, all these events, when these curators were measuring them, they went and looked at all these news articles manually, and they said, oh yeah, these are the typical events that happen. But what if we can automate this? If we can automate this, we can automatically calculate the likelihood of these events. So what we did was, we used a big news corpus like GigaWord, which is essentially news articles for the last 100 years. And first we did an information retrieval for the term riot, just to take this example. From each such news article, we pick the top N. Then for each passage or paragraph in the news article, we ask GPT again for entailment. For example, return the answer in one word. That's the passage. He says correctional officers opened fire as they tried to break up the riot. This is from a typical news article about a riot that happened in a prison. Does that passage entail, contradict, or is neutral to police attempt crowd control measures? So this is like the double for loop that went on for every single passage, trying to connect and entail it with the events in a schema. So once we had that, we were able to calculate the rest of the parts in this equation using probability of passage given news articles and how many news articles do we have, what is the relevance of it, the probability of it, and the probability of passages from the whole, news articles from the last 100 years. This is the more interesting part. So let's look at some qualitative results. So here we asked like each of these models, right? The GPT, a human, and our framework. We asked which are the most likely events to occur in a riot. So GPT says, hey, here are people gathering, rioters destroy property. So all this were created by the suggestions from GPT. Humans kind of say the same thing. People gathering, they agree, right? They agree like rioters disperse is agreed here. But humans said, no, hold on. There's one thing which is rioters improvise weapons. So that was one of the predictions. But our framework did not agree with the rioters disperse part, but it added rioters attack people. Now, how many times does it happen? That is exactly, we provide a likelihood score for that happening. So the basic bottom line I'm trying to sell here is that we are trying to get rid of this human in the loop, and we are still trying to put a value to that individual event automatically in a probabilistic schema. So again, of course, the same downstream tasks. If you know a person is buying ammonium nitrate, what is the probability of him committing a suicide bombing attack? Now, granted, there is a component of psychology and the person's history in there, but these are potential things that can happen in the future with this kind of an automated methodology. The same example I showed here. Another interesting possible downstream task we discovered was an automated system for ranking predictions of GPT or large language models. So this is the example I showed you earlier. These are the events that typically happen in a riot. Tell me which was the first one. Social unrest intensifies, GPT says. I ask again, it says a different thing. Public dissatisfaction grows. So this was typically, as you know, like the non-deterministic reply of GPT. How do we put a number to it? Like how do we even know this thing? How really likely are these things to event? Exactly what our tool did. So given the prompt and the response, the tool is now able to calculate, oh yeah, 0.86, there's a possibility that social unrest intensifies. So this is grounded against news articles from the last 100 years. So this is what we have been able to achieve, not just a score calculated for likelihood, but this is useful in kind of explaining or re-ranking the replies of a otherwise black box model. And again, this is what I was saying. If this works, we don't need to have that human there. We cannot, if this is well established and if the likelihood scores continue to improve, then we can probably get rid of human, and this can go towards an automatic schema curation. So this is the underlying theme in my research overall, is explainable AI. So how can we get some sort of explainability or interpretability from all these large language models? Now, with that single pitch there, I want to introduce something known as quantum NLP.
Can I ask a question?
Yeah.
So you quick, did you come up with the scores based on the 100 years of text that you have, or by some other method?
From the text. So this is, the calculation is from the news article text right here, like this.
What was the model? The baseline method that you used?
Yeah, the same thing here, right? So instead of the Bayesian one, we just, instead of schema and event, we now replace that event with a passage and a schema with a news article.
What was the model you used?
This is a probabilistic model. Just
Can you be more specific?
PM25 for IR, just calculating the total number of news articles divided by the number of entailments. So if you remember, there's an
retrieve news articles that match the keyword
riot, right? And then we are still using a large language model to do the entailment for us. So the entailment is simply done to understand if a given news passage maps to any of the riot events that happened. So if one event maps, we consider the whole document as entailed, and then that goes into this particular probability of passage and probability of passage given news article calculations.
So, but specifically, you're looking to see whether social event or whatever social arrest intensifies.
Correct.
Happens. So that's what you retrieved.
Yes.
Right. So presumably, one factual clarification. You keep on saying the gigawatt is 100 years old, or sorry, covers 100 years of data. I'm pretty sure it's 10 years of data.
No.
94 to 2003. But anyway, you should look that up for.
Maybe you're right.
But also, I wonder, could you also just ask the Chat-GPT itself to give you the probability of that statement, given that gigawatt is presumably part of its training data?
Yes, that also opens a complex can of worms, which is basically if GPT already saw this data during training, and if you're asking it to already predict it, right? So what is that fair prediction?
Well, that's the same question that I would ask about this to begin with, right? Because you're validating the decision of something that is trained on the same data, with the same data.
And another related comment that people have tried, like computing probabilities directly from the model outputs. Like for instance, ask the model 100 times. Let's see what its rates like in what's the frequency of the same output coming up, and that's like a proxy for this is more likely to generate for the model.
No, I actually in the paper I did have an example like, okay, hey, here's what my model said the probability is, but just give the probability for GPT itself. What does it say? So yeah. It's for the equivalent of it.
Yeah, might be interesting to just have a comparison of how calibrated those probabilities are compared to this.
I mean, my problem with that is still it's a black box. There is no way to find out how GPT is arriving at that number.
Yeah.
Slight explainable angle to it is more explainable from a human perspective. At least I know how the numbers are calculated exactly. Okay, so let me go back to the same example. This was again the same scenario which came from the initial DARPA idea. Person buying ammonium nitrate, there's a machine learning model trained there to identify this particular scenario, let's say, and the model says, oh, he's definitely going to commit a suicide bomb attack. He needs to be neutralized, but the model does not give you an explanation. So the question I have been asking is, if you are a field commander and if you are taking assistance from an AI model, do you kind of just blindly follow that, especially when it's not really giving all the steps that it used to arrive at that conclusion during training and during prediction? So that is the first scenario. Second scenario is this, the reverse of this. Say there is a report containing clues about an immediate dirty bomb attack. We again have a machine learning model which is trained to identify this. However, the model does not identify this, and it doesn't flag that there's a dirty bomb attack happening, and the event actually happens. So why did that happen? That's because there's actually very less prior data on dirty bomb attacks. So the model has not seen enough context in general to learn these are the clues towards a dirty bomb attacks. So my basic goal right now is, can we have AI models which are interpretable, right? Interpretable is, like I said, my definition of interpretability is I want to know what it was learning during training and also the steps during your prediction. Can we still have models which can learn even when the historic data is sparse? So if you think about it, as humans, we really don't need so many of that examples of dirty bomb, right? If you learn what a dirty bomb is and you associate, oh, this is a dirty bomb. So there is some human learning that is missing here. Like, what is the differentiation between a machine learning definition of a dirty bomb from all the words around it? And how is human when he first understands what a dirty bomb attack is? So these are the questions pertinent across my research everywhere and which I've been asking. So can we create a model and which is how I encountered this thing, the QNLP, or the quantum natural language processing. Now, history here is this was originally created for machine learning for NLP using quantum computers. But then we discovered recently that this can work very well on a classical machine, like everything runs on my laptop right now. And more importantly, it incorporates, all right, let's see. Okay, let me get to that point in a second. So typically the same pipeline happens in a quantum computer. Okay, if you just look at natural language processing, learning that happens in a quantum computer. The quick introduction there is, if you are not familiar with this, we have 0 and 1 as classical bits, but in a quantum world, 0 and 1 is only one of the million trillion possibilities that a qubit can take. So that idea alone is essentially what is being used in these kind of frameworks known as quantum NLP. This is the major difference. This particular model, quantum NLP, it incorporates compositionality, or in other words, grammar fundamentally into the training process. So if you think about the history of machine learning, there are two major schools. One is the compositionality school of thought, and the other one is a context school of thought. The context school of thought is what we are very familiar with, because in the last 10, 20 years, everybody was going through the idea of first paradigm, which is a word can be measured by the company it keeps. And from where bag of words came out, neural networks and all the large language models. But before that, there was a time when linguists were insisting there needs to be an amount of compositionality incorporated, because they are looking at it from a different perspective of human learning. The way a human learns languages, not just from the examples, which is the context-based system, but there is also a component of compositionality. Let's say you learn a language where you first learn the meanings of these individual words, and then you build it up together into a new, using grammar, into a new meaning space. Say, for example, you know the person John, not John, but John, random John, John, and we know what park is, what the word walking means. The moment you hear the sentence, John walks in the park, now you have a new kind of meaning that is coming in your head. So that is the kind of measurement which the quantum framework is trying to capture. Can we incorporate meaning fundamentally and build it up from there? So like I said, one side is the quantum side, which is purely compositionality, and the right side is context, which of course we know as large language models and their further advancements. Now, let me give a quick example of how machine learning is done on a quantum computer. So as you know, machine learning, typically what happens is we have an input layer where we currently, let's say, provide the embeddings, passes through a hidden, some sort of a hidden layer of neurons. We predict the values and we look at the difference and we do backpropagation. So this is essentially the core of any neural network-based model. There are architecture variations to it. But the fundamental point here is, when you do backpropagation, essentially we are learning weights, which are weights of these neurons and not the weights of the input terms. Like, we cannot really put a number to John walks in the park and we say, what is the weight of John? And that is the interpretability question, right? How do you map a neuron's weight to the actual word there? The reason I'm saying this is machine learning using quantum computers are exactly the same. The only difference is instead of the neural network architecture, there is something known as quantum circuits. Like, everything else remains the same. Like, input comes in as words, something happens in a let's call it a random black box architecture for now. The model makes a prediction, looks at the difference between the prediction and the goal. Again, backpropagation happens. But the major step difference here is, the first part is where you convert a sentence into its grammatical parse diagrams. And the idea here is that when we start still with the embeddings of John walks in the park, separate each of these words, we get the meaning of it from one of the standard embeddings, could be even GPT embed. So we are grounding and starting with the meaning and composing it into a meaningful sentence. That is a core idea they are using here. That is, we add grammar into this, which is actually composing it into taking it to a new different plane of thought. That is a core idea without getting into the details of the quantum part. And the second part is, a circuit, like a neural network, let's call it an equivalent of neural network, is automatically generated for a given sentence. So this is the most important part. For every single sentence, we have a new circuit that comes out. So these are like standard gates, like just any circuit you would know from engineering days, like instead of a NAND and AND gate, it just creates, an equivalent of this will be, it just creates a neural network architecture. But the most interesting thing there is, these circuits are directly mapped to the word. So here you can see this gate here, like these are all gates, like a NAND gate. This gate is for John. This gate is for par, in. So these gates are directly mapping to the word. So the weights actually are the weights of the word. So that is how the QNLP is looking at it. We're essentially saying that we are going to not just learn weights of a bunch of random gates. We are going to learn the weights of John, weights of walk, weights of par. And that is the one which is going to evolve across time. And the reason I mentioned qubit is, a qubit is capable of remembering all this at the same time as opposed to a single classical bit. So, like I said, sorry, go ahead.
So the structure of a quantum circuit, is it dependent just on the parse of the sentence or on the vocabulary as well? So like if I had the sentence, Mitch runs in the park, would that have the same circuit architecture as John walks in the park?
The circuit architecture remains the same, but so there are these RX is essentially standing for angle of a gate. So this is so let's imagine a gate to be like a blob of sphere, and the weights are essentially angles. There's like let's say there's a clock-like thing inside a three-dimensional sphere. So the meaning, like we initialize your embedding vector, we have an initial weight value. So that is the clock is pointing to 12.3 some angle. But if John gets replaced by Mitch, that the clock value changes because the meaning is differently pointing, but the circuit still remains same because the structure is still the same of the sentence. So that's why we are incorporating meaning and structure at the same time.
So the weight of a node would change, but the connections between nodes,
if it's the same kind of grammatical structure, it remains the same. And this happens for every single sentence, and which is the brilliance of qubit, because you really need like maximum number of qubits you need is the maximum number of words in a sentence in the corpus. So if 10 was the maximum number of words, you just need 10 qubits, and that's all you need. If the sentence was 10 words long, you just need 10 qubits to do the whole process. So that is the physics part of it, which I don't have enough time to get into. So the major difference, like for example, if you want to really compare classical versus quantum, so instead of embedding per sentence, we have circuit per sentence. Instead of weights, the angles, which I just mentioned, and the output is exactly the same, predicts a value, back propagates, tries to find the difference of the value, and updates the angle of the weights. So the idea here is it builds interpretability bottom up by learning weights corresponding to words and not neurons. So let's take an example. Alice loves Bob. This is the evolution of the weight of the gate corresponding to Alice. You can actually see that you can trace the weight, not just, let's say, if you were equivalent of this was, bird, 12th layer, 13th neuron. Yeah, you can find 12th layer, 13th, sorry, there's no 13th, there's 12th layer, 9th neuron. But what does that mean from a semantic perspective? So this architecture is so deep in semantics that, let me give the counterexample to this. Alice not love Bob. The weights of not is actually on a negative angle, that you can actually see the semantic equivalent of it, right? The only difference between Alice loves Bob, semantically meaning-wise, and Alice does not love Bob is the not. It flips the meaning in your head to a negative side. So that it is that level of details that you can see during training itself.
Quick question. What's the analogs for like getting contextual representations here? Like the goal of when your networks in general was like, hey, start off from word representation, then you have more contextual embedding of the sentence, that we would not be able to like trace back to individual words, but we would have a contextual embedding of the whole thing. So in this case, what's the analogs for that? And is that not something which is used?
So there is
the final prediction?
No. So at this point, it's basically the idea here is instead of context, we are using compositionality at that point. So now the catch here is, right now at this point, the state of the art in quantum world is essentially given one sentence, it understands only the meaning of a sentence. There is no cross sentence learning at this point doable. And that is where context helps, right? If you have one word and the context around it in a sentence, we still can have, let's say LSTM kind of thing where you have long distance memories between multiple sentences. So that is not yet achieved. So that is not there, but right now the focus was on compositionality and just the fundamental meaning of it. And their idea is by merging this into a flow of information between the words, we are able to get the meaning into actual space, like what a human thinks of given a sentence.
So I have some problems already with the idea of not meaning negative always in this way. But let's set that aside. Why would Alice be positive?
Oh, just initiated. I was just comparing the values of one with the other, and I discovered one is exactly opposite of the other.
But that doesn't mean that you've learned semantics. You've just found that two things have different values.
Correct.
So I still don't. Also, you would say that, okay, you can look at the 9th neuron of Alice, of the 12th layer. That's true. But you could also take, and maybe that itself is not interpretable, but you can also take the entire representation that is on top of the token for Alice and look at the entire representation of the token that is on top of other female names and see if they have a high cosine similarity versus not. And there's definitely work that does that from word to back on. So, I mean, it seems like there's some, to the degree that there's semantics here, I would argue there's definitely semantics there.
No, I agree.
I might also disagree that there's semantics anywhere, but that's a separate issue. I don't see the argument for why quantum has a better.
It's not better. That's my point. I'm not even coming towards it's better. All I'm saying is, right now we have post hoc methodologies, which is we have the model trained, and then we go back probing in and trying to find the meaning of something. So my thought at this point is, can we also incorporate a bottom-up approach during training for meaning? Like not just wait for these things to finish training and then probe backwards. That is where I'm going with this.
Is the point that you get the converged value at like a little after 200? When you say not wait and then go backward.
Yeah, so at the end of training itself, you have a record of where all the qubit went through to understand its evolution of meaning.
Okay. So what does this graph tell us?
Yeah, what's the y-axis?
Y-axis is just epochs and steps. Oh, sorry, x-axis. Oh, the angle of the gate.
Okay, so you said that you can go backwards and tell the story. So what is the story?
The story here is you started with the meaning of Alice, which you took from embedding, with standard embeddings. And we found that after going through all these multiple events, it has converged on some meaning of Alice. We don't know what the meaning of Alice is, but at least we can see it evolving. So
we also see that if it was a transformer?
From the weight of neuron?
From the let's say the vocabulary embedding.
Fair.
I mean, it changes over time.
Okay.
Much is looked at the evolution of various parameters in RNNs, for example, and imagine similar kind of things can be true if you're especially just looking at the vocab table. But
okay, fair point.
But I still don't think we can draw much of a conclusion from it.
Okay. What's your question?
So this is often hinging on the quantum circuit, like Frank communicates being reversible, right? As going through the back to find your weights, right?
Mm-hmm.
So then do you actually need a quantum computer to do that, in the sense that in a classical computer you can do the same?
Yeah, which is why I was running this essentially on my classical computer, because the equivalent of that is a PyTorch model, right? So the point is the sheer amount of resources I need for this is different than just 6 qubits or 10 qubits.
But what you're gaining here is space, not time, right? So you're talking about 10 qubits being the length of
correct.
The structure.
But incorporating grammar level dependencies and compositions into a non-bag of words kind of model is space mainly, is the constraint.
But there's no quantum algorithm where you're gaining.
No. it's not a quantum advantage. It's a different software framework looking at things. So it can be run on a quantum computer, it can be run on a classical computer also.
But what you're saving is that classical space.
Yes, the space, which was a problem earlier when people tried injecting dependency parsers into as a feature engineering. So it just explodes out because you keep having this subject verb object kind of thing, keep adding that. So which is why we discovered bag of words still does a good job. So anyway, let me get to the point I was trying to make, right? So all of this, more importantly, this is some of the experiments I ran, right? It still yields a high performance in low resource setting. Let me give an example. Let's take the natural language inference corpus. So this is, so natural language inference, for people who don't know, is given two sentences, Alice loves Bob and Alice does not love Bob. The goal is the model should predict whether they entail, contradict, or are neutral to each other. So in this case, of course, they contradict with each other. So what I did was I took a bunch of random training points from 100 data points from standard natural language inference like Glue, and I trained the model just on 100 data points and tested it on 20 data points from the same data set. And I did that for various models, including Roberta Large, and the other two ones are from the Hugging Face state-of-the-art model, which gives the highest performance for MNLite, or Glue, which is including the Glue data set. And you can see that in this kind of a very less resource scenario, these models really are not able to train very well in just 100 data points, while the other model is able to do a good accuracy. Take it to the pinch of salt. These are like one experiment I ran. I still need to verify this across. But I am wondering if this is because really to learn a meaning of something, you just need a few examples and not a ton of it. If you think about it purely from a meaning and compositional perspective. If you go only from a context perspective, that explains why we need tons and tons of examples and context to understand the actual meaning of a given word.
What are the two models in the middle?
In the middle, I don't know the names of it. I can point you in from the Hugging Face repository, which is there.
Oh, this is like fine-tuned.
This it actually fine-tuned on these just 100 data points.
But this is, and then evaluated on how that does test that?
Evaluated on the random test set of MNLI itself.
And in QNLP, you said you start with some embeddings. Right? What were the embeddings used in the QNLP?
So this experiment was fast text, just very similar to how the original byte pair encoding happens. Fast text was the kind of original, it takes A and D, the word and splits into A, adds an N, adds a D to it. So that's the original kind of idea. That was the particular one it was used in this case.
Do you get a chance to compare with using the same embeddings with like a simpler or different model design, more classical model?
No, what is the point? Sorry.
Like just comparing, like I'm just getting a sense of where the improvement is coming from, the way you're designing.
No, surely, yeah. There's a lot more experiments I need to do at this. Just a few thoughts and ideas I got when I got this initial. So as a proof of concept, I tried it again on a different task, text classification. The task here is, Alice is making lasagna. Is it food or technology? The goal is, it's a food. Same thing, trained on 100, tested on 20. Roberta Large is 0.63, while this model is still giving 1 accuracy. So just to pick your interest, just to pick my own interest, there is something in there which I still don't know exactly to answer every question of yours, why it's happening. There's something there with the grammar and the compositionality going on, which
Is QNLP very slow to do inference?
Which the
QNLP. I'm just wondering why your test sets are so small.
Oh no, that's only because running that in a quantum computer for me was more trickier, because even the problem there was the machines which I use are the Saga cluster here, which is in turn posting to a quantum computer. But Saga cluster was giving up on the sheer amount of information that's coming from a quantum computer. So that is the bottleneck at this point.
This is truly running cloud, it's not on a simulation.
It's not on a simulation. It actually took me a day or two for, if you look at an IBM cluster of quantum machines, which they actually is publicly available, quantum cloud, it's scheduling. It's basically you submit it today, you'll get it like a day or two back because there are only few of them publicly exposed. And also, the publicly available ones have like 5 qubits, while the state of the art is 120, so which you have to pay for. So I again had to like take only a subset of MNLi, which would run in these machines. So granted, this is all like a little bit of hacky stuff, but just wanted to make a point. There's something in there. Anyway, sorry, question? All right.
So I had a question kind of on, I guess, like application of this. So obviously quantum computing is expensive because there's not many computers that have to be so cold and stuff. So is it actually worth it, like from a cost or energy perspective, or is it more cost effective to just use more space and time on a classical computer?
If you can use more space and time on a classical computer, yes. But right now we don't have models which incorporate grammar. At least I haven't seen any in the post-GPT world, which is everything a bag of words. So again, I don't know the answer to that. It's proof is in the pudding. 5 years later, we will decide with all these possible experiments run. Almost out of time, right? Okay, let me crack up. So there's possible implications in military where explainability is important, in medical field where we have to predict chronic diseases, legal field where you need an explainability for legal decisions. Let me quickly finish this where I'm going with this, right? So just the stuff I've been wondering and talking to the wrong person, which is Ulf, about the history of humankind and languages. So if you trace the history of humankind, this is well known that humanity started in Africa and we moved out of Africa 170,000 years ago. And around 65,000 years ago, a split happens there and people move all the way to different parts of the world. So there are 2 major theories about origin of languages, 2 major schools of thought. The first one is discontinuity, which is the very first line here, which says, hey, this thing that happened here in 65,000 years ago was a divine intervention, suddenly happened. And then that's a discontinuity part. And the continuity part is, okay, there's one more example of discontinuity, which is the last one, which is genetic source, automatic set of developments in the young human children. That is a discontinuity school of thought. And there's a continuity school of thought, which says, gradually we found onomatopoeic words. We say sh for sh, and we started calling it ish. And there are arguments for and against it. Okay. And just to say grounded, Chomsky is a big believer in the discontinuity one. And he says around 100,000 years ago, a chance mutation occurred in an individual and suddenly humans acquired language. So still being argued. So I've been wondering this, what happened to human around 100,000 years ago. So there is this research we talk about Adamic language, which is essentially a mother of all languages from which stuff happened, which is, if you compare biblically, the Tower of Babel happens, and then humans were, if you want to believe that, humans were distributed into different languages. So I'm approaching just this curiosity question from a language perspective, because the known history of languages stops, like the root is Indo-European, and Indo-European is after that 65,000 years ago. So, and then we have pure history from there, how every language evolves. So I'm saying all this because are we at a moment where machines we make can do language acquisition of its own? So we are probably at the same point where, we are at a moment similar to sudden language acquisition epiphany for humans, where machines we make, are they suddenly becoming intelligent? Or are we going towards this kind of a place considering everything what GPT is doing? And the question I'm bringing here is, how do we even know if the model is learning and understanding a language? So can we do this by providing a compositionality along with context, just injecting some kind of a guide rail in the training process so that a human also is kind of understanding how the training is happening? Again, like I said, are LLMs really understanding what they're learning? How can we tell? We have currently post hoc methods, most of them, what John mentioned earlier. We look back at it and see, we can trace it back. But what if we can inject this also during training itself? Yeah, so this is my point, like if you can inject. So yes, we have, if you remember, like knowledge graphs is exactly doing kind of the same thing there, but what if kind of the same thing knowledge graph is doing, but what if we can just inject it in the beginning itself? Yeah, if yes, we can get to 42, which is the answer to life, universe, and everything. If you guys have Douglas Adams' history, just wanted to say thank you for all the wonderful people, my wonderful mentor Marjorie, Ralph, John, Jen who's here, Elena, Wolf. I couldn't find a picture of yours. You're a secretive person. So thank you, everybody. Yeah, I had a wonderful time at ISAC. Thank you.